All right, so yeah, thanks for the introduction, for the invitation. So the first time I came to this city, Pisa, was almost 7 or 8 years ago when I was a graduate student. I visited Florence with a friend, and then I decided, okay, I have to see the tower. So I came here for the afternoon, and so it's great I can be here for the entire week and see the tower for thousands of many times. Okay, so yeah, all right, so today I'm going to talk about, but not only today, but actually the next 5 lectures, I will be talking about the decomposition theorem for abelian fibrations. Of course, I will introduce every term which showed up in the title. And I know this is, it's very hot in summer, so I hope everyone can survive. So, including myself. So I will start with an overview and the motivation. In particular, let me start with a few minutes addressing the question, what kind of geometry we care about, or what kind of question okay, is it too small for people there? Okay. So the geometry we treat, I mean, from the title, they will be abelian fibrations. So roughly speaking, they are fibrations whose general fibers are abelian varieties. So I will explain why, in this case, it's more interesting, or it's more, manageable. And then the special fiber could be very, very complicated. So let me give a cartoon of the geometry we would be dealing with. So okay, so we consider a tower over a base. So x over b, so usually this will be proper. And most of the time it even will be projective. So there will be relative ample line bundles over it. And then, so for the geometry we care about, usually the general fibers are nice. So let's write an open U, which is open dense, over which the geometry of this tower is well understood. Okay, so let me just so this part will be smooth. However, the complicated situation usually happen at the boundary of this torus fibration. Okay, so let me just write this. You have a complicated Z. So this is usually closed of lower dimension. You can think of this Z as the discriminant of the morphism. And then over which you have a very complicated geometric object. So okay, so you can also consider the fiber product over Z, which is this morphism. Of course, it's usually our main interest, but it's very interesting. It's very complicated, not smooth, and most of the time complicated. Okay, so this is the cartoon of the geometry we would be dealing with, and the techniques we discuss during this week, at least in my lectures, will be about how to treat the entire geometry or even these bed fibers using the information we obtain from these good fibers. And the reason I chose this topic is because, yeah, I will say this in a minute. So there are many questions which have different phases, but they have something in common, which is this picture, and I will discuss some of them before moving to the more detailed discussion. So I just drew this picture, but let me discuss the features. I write them in words, features. So first, the space we care about, features of the geometry. So the space we care about admits a fibration. This is the word abelian fibration means, admits a fibration over a base. And we have to have some good understanding of the fibration. So a general fiber is smooth and easy to understand. I will be more precise about it, of course, later. Easy to understand. And most of the time in these lectures, a general fiber will be abelian varieties. So this seems to be a very philosophical reason, but actually it's a technical reason why I will explain precisely why having the abelian structure can actually help us to understand the structure of the decomposition theorem much better. So most of the time of these lectures, so the general fiber will be abelian varieties. And of course, the main difficulty usually lies in the special fiber. So the special fiber can be very complicated. So, but our purpose, so the question usually is about the entire geometry of X over B, and what we can understand as XU over U, and the purpose is to understand X over B without knowing too much about over this Z. So the Z is over Z, everything is complicated, and these are ugly fibers, and we don't really want to, in most of cases, we don't really want to, more or less most of the time it's impossible to get a dictionary or get a full information of these fibers. So the purpose is to, we want to understand the cohomology of X, namely the total space, in terms of the smooth fibers. I guess in other lecture, for example, Economics lecture, we will try to study something more than cohomology, for example, derived categories and more complicated invariants. But for the purpose of my lectures, the main invariant we care about are cohomologies. So the main two, of course, so these are the features of this geometries we care about, and I'll give you a list of examples. But before that, let me drop some words. So the main tool, of course, will be, okay, so we want to use the smooth fibration to study everything, and one of the key tools, of course, is the decomposition theorem of Beilinson, Bernstein, Deligne, and Garber. Which for the rest of lecture, I would only use BBDG. And the decomposition theorem is a very powerful tool, which mainly is about the existence. If you look at the statement, this is mainly about the existence result, not the computational result. And it is after Engels' work about 15 years ago, who really tried to, in the case of abelian fibrations, he initiated a very powerful tool of doing computation, which I will discuss, the Engels support theorem. So there are two tools, the general theory of the BBDG, decomposition theorem, and also Engels support theorem, which works particularly well for abelian fibrations. But of course, these are the two general tools. Every time you see an abelian fibration, for example, like Hitching fibration and or relevant spaces, then you can try to apply these tools. But usually, in order to solve a problem, you need most of the time you need more. But these are the structures that showed up in common. So plus more maybe. Okay, so this is an overview of the thing we will be dealing with. So before moving to technical details, I will give you a little more motivation, namely examples. Okay, so I hope I can erase this part, because the picture is simple. You have a fibration with nice smooth fibers, complicated singular fibers. So as I mentioned, the reason I chose this topic is because this really showed up a lot in actually several different questions I looked at. And of course, as I said, applying these tools, they may not give you immediately the final answer. So you need, for every different question, you need some extra input from that question itself. But these are the tools that which showed up in common. So let me discuss them. So example 0. So since this is the non-technical part, so later I will move to the technical discussion. So let me just do this briefly. So the first result, of course, so how this is applied is in Gauss geometric stabilization. This actually played a very important. This is the main geometric input in his proof of the fundamental lemma in the Langlands program. So this is how he cares about and why he developed this tool. So let me just draw the picture in an oversimplified way to illustrate the idea. So the question Ngo cared about, so he reduced the proof of the fundamental lemma to such a situation where you have two fibrations over the same base. So x, of course, in his real setting, there's more technical terms, but let me just do the more conceptual way. So you have x and x prime, which are certain Hitching fibration, which I may not introduce now, over the base B. Okay, you have the same base, and you have two different geometric objects over it. And so by some not simple, but by some analysis, one knows that there exists a Zariski open U over the base such that if you consider those fibers over this U, so you can consider the fiber for the first fibration or the second. And if you count the number in finite fields, they give you the same number. So if you do point counting over xb and x prime b, it's the same number. So this is what you know. And what you want is, you can imagine these are the match for the counting over like the good fibers. And what you want is for any b which lies in the boundary concerning these complicated fibers, and you want this to hold the same hold. And in order to treat this kind of situation, then Ngo developed, so now it is called the Ngo support theorem. So I mean, after these lectures, I still hope everyone who is interested to look at the original paper. So this is in his fundamental lemma paper, which is, fundamental lemma paper, which is very long and in French. I don't know. I don't think this is a problem for many of you here, of course. And chapter 7. So each chapter deals with I mean, the first few chapters are more theoretic, and then the chapter 7 is geometric, and he explained how to deal with this kind of situation. So okay. So in particular, after introducing these techniques, we'll be because counting points over finite fields can be viewed as a cohomological thing. Because you can if you understand the cohomology, then you can just take the Frobenius, and this gives you the point counting. So in particular, this question essentially concerns that understanding the bad fibers using the good fibers. Okay, but actually, of course, there are more. Okay, let's go to the example 1. So this concerns a slightly different but a similar situation, which is the topological mirror symmetry. Conjecture of Hausel and Thaddeus. This is a question which was proposed by Hausel and Thaddeus more than 20 years ago, and this was first proved by Gorenik with Ziegler using p-adic integrations. And then later in the joint work with Davesh Maulik, we gave a proof along this line. So yeah, the question is similar, of similar flavor. So again, let me just write down the picture. So f and f prime, and you have some u. So the picture are sorry. So here x and x prime are the Hitchin system. Over the semi-stable part of the Hitchin system. The semi-stable locus of the Hitchin system associated with the groups in type A, SLN, and PGLN. And we know that it is not very hard to show, this was actually essentially done in the original Hausel-Thaddeus paper, that if you restrict yourself to some open subset, they are dual torus fibrations. So if you consider the relative cohomology, so of course I'm simplifying something, but so this is not exactly true, but you have to interpret this slightly correctly. But roughly speaking, you have if you can consider the push forward of the constant sheaf here, you consider the push forward constant sheaf here. You don't know whether they are the same. But you know that they are the same if you're restricting over this u, because these are, very nice. These are the very nice objects after restricting over u, so you know they are the same. And so in particular, if you have a push forward and push forward, they are the same, then you take global cohomology, you know that if you just remove all these z, the complement of B, the u inside B, and we know immediately that the cohomology of xu, the nice part, of course, is isomorphic to the cohomology of the nice part over the other fibration. However, the thing you really want or this is precisely what they conjectured, is that it's not a statement which is only true over the nice locus, but it's a statement which is true homologically and globally. So this is these two pictures look similar, but technically, actually, they're quite different. In goal setting, he mainly considered, for example, in this SL PGLN case, he mainly concerned the spectral curves which are integral, whose fibers are better, and how the set is considered the entire. Since the motivation is topological mirror symmetry, they have to consider the entire modular space of semi-stable locus. So you really have very, very complicated fibers. Even the fibers may not be integral, and the fiber may not be even reduced. And in the later part of the lectures, I will explain what are the possible techniques in treating this kind of situation. But okay, so but in one words of explaining of describing this phenomenon is what? So you have a match of the cohomology over the smooth locus, over some good locus. And you want to say, okay, so the boundary could be complicated, and for x and x prime, certainly the boundary are different. But it doesn't matter. So no matter how it's like you do a partial compactification over U over the entire B, and it doesn't matter how the compactification looks like. It seems that homologically it's not influenced, it's not effective. So morally this conjecture says that the boundary will not destroy things. So if you have an identity in the nice locus, it remains an identity over the boundary. Okay. Okay, so this is more or less the first set of examples concerning the match of different Hitchin systems. But actually, as I mentioned earlier, this phenomenon really showed up a lot. So let me give you some other examples to motivate you to survive through the lecture series. Because example 3. Okay, did I lose counting? 0, 1. Okay. Yeah, 2. Okay, so this concerns another a geometric object, and this is actually, it has a great contribution from Italian algebraic geometry, Italian school of algebraic geometry. So this concerns the compactified Jacobians over the model of stable curves. Okay, so the main reference for this is due to the work of Migrolini, Schinde, Viviani. So, okay, so let me explain what kind of geometry we're interested in. So consider this concerns a more classical geometric object, which is the Deligne-Mumford compactification. So this is the Deligne-Mumford model of stable curves. Deligne-Mumford modula of stable curves with n-marked points. So a large part of algebraic geometry actually in the the classical algebraic geometry considers that, okay, people have some statement over MG that you have statements for smooth curves, and people wanted to understand what happens over the boundary, and there is a very natural compatification using nodal curves. So a curve inside, let me just draw some picture. Yeah. So this is a stable curve. These are the nodal singularities, and you have some marking. Okay, so this is yeah, I just use a color chalk. Okay, so this is a curve in genus 1, 2, 3, 4, 5, and also 5 marked points. Okay, so then over MG and bar we can consider, so over MG, so one can consider the universal Jacobian which parameterizes. So for every curve you consider Jacobian, and when you vary the curve you have a family of Jacobians. And okay, so one of the very natural questions in algebraic geometry is to compactify this over MG and bar. So when the curves degenerate to these types, what happens to the Jacobian? And this is a subject which has been studied for decades. So, however, so in order to get a good model over the entire MG and bar, so one has to choose a stability condition. So about what kind of sheaves you want to put on the boundary to compactify it. So so this is this phi is a stability condition. And so this is parameterized by some space of stability condition where there's a wall and a chamber structure, as you can imagine. So when you lie in a chamber, so there's no strictly semi-stable, so that the model is a smooth Riemann stack. When you go to a wall, then some contraction will happen, and then the geometry becomes worse. So this is the space of stability. So you have phi 1 here, phi 2 here, and so on. Okay, so it's a complicated picture because if you want to study the universal Jacobian over MG and bar, you have to choose a stability condition, and many things will be dependent on it. And as long as the genus and the marked points getting more and more, then the space of stability conditions is becoming more complicated. So in particular, so every time it's annoying, right? So every time you want to study it, you have to pick a stability condition and study the geometry with respect to that. And so, but actually this step it cannot be avoided because the geometry of this compactified Jacobian, let's give it a name. Yeah, it's a compactified Jacobian. So it depends really on the choice of phi. So if you choose different phi, you will get different varieties. However, what they showed is that, so they saved our life by showing that if you consider, well, this is actually a consequence of their result, which shows that if you consider their cohomology instead of the variety itself, it doesn't depend on the stability condition. So so the cohomology as a Q vector space does not depend on phi. Okay, so again, so I describe this question using like 1.5 blackboards, but actually this question can also be described by one sentence, which is that the boundary does not destroy things. Because if you, oh yeah?
It does not depend on phi, provided
Right, so it's, yes, non-degenerate. Yeah, thank you. Meaning that it's not on the wall. But I just want to illustrate the phenomena. I didn't, but it's a very good question. Thanks. I didn't want to go into that technical term because for every question, every example I illustrated now, if you want to, if you want to go into the details of discussing it, it will be at least 1 hour lecture. So, but I want to just give you the showcase that this is actually a very a powerful tool which can actually be treated in many questions. So again, so this phenomenon also suggests that the boundary, this is the phenomenon that the boundary does not screw things up. Although you see that when you change the stability conditions for a smooth curve, the Jacobian is the Jacobian. There's nothing much you can do. But when the curve is broken like this, that there might be different choices and assignment, but there's some technical tool which can help us to show that if you consider cohomological information like in like in this blackboard, the boundary actually doesn't matter. Okay, one more. Example 2, sorry, example 3. So far we have been talking about cohomology. Point counting over finite fields can be viewed as a shadow of the L-adic cohomology, and here we concern singular cohomology. But actually, the techniques here can also be helpful for us to understand algebraic cycles, which are like the generalized cohomology. So these techniques can also be help us to treat the standard conjectures for algebraic cycles. So to give you some examples how these ideas work. So there's a work by Cavici, Latvier, Saka, so who treated Lefschetz standard conjecture. For certain Lagrangian fibration with integral fibers, and there's also a recent work in the joint work with Maulik, myself, and Qi Zhenying. So we use the support theorem to prove the motivic, the Cauchy-Hanamura's motivic decomposition conjecture. For Hitching system. Okay, so the question of this kind looks slightly different with the ones we talked about earlier. So let me say, probably I won't have time, I mean, even till the end of the lectures, I won't have time to discuss the phenomenon for algebraic cycles too much, but let me give you some idea why these cohomological tools actually can be helpful in understanding algebraic cycles. So again, you have a fibration, and then you have some locus over which the fibration is well understood. So the situation, usually the situation is the following. So we can find algebraic cycles So this standard conjecture, the statement usually is that, so the statement is that you are able to find certain algebraic cycles which act on cohomology nicely or as expected. So we can find algebraic cycles, say Z over the relative product over B, such that, okay, the fibration could be complicated. It's very hard to calculate it. But if you restrict your cycle over this U, this is a nice fibration. So this is an algebraic cycle over XU cross XU over U, and we know how it, such that the action on the cohomology of the smooth part is expected. So this is, let me say, just say nicely. However, so the main thing we want is that the cycle we constructed actually acts on the entire cohomology of X nicely. Okay, so usually this is the pattern for proving these conjectures. So you start with the construction of a cycle somewhere, and then you first, you get your cycle, and then you want to show that this cycle acts on the cohomology as in the expected way. But it's very hard to show this because the cohomology is usually is a very large vector space, and most of the time it's very hard to calculate it in explicit correspondence. But let's assume that you can handle what happens on cohomology over the nice fibers. And then the upshot is that by suitable ways of applying the techniques I'm going to discuss, you can show that these cycles really act as expected in an expected way over the global cohomology. So again, you can imagine this is some sort of, the boundary does not destroy things phenomenon, but in a slightly different manner. Okay, so these are, I've listed many examples. They concern Hitching system, model of curves, algebraic cycles. So the one thing I want to emphasize is that this phenomenon, the sentence I wrote in this quotation marks, it happened a lot in abelian fibration situations. For example, in the proof of the proof with Davish about the topological mirror symmetry for SL and PGL Hitching systems, and also in our proof of the P equals W conjecture, and that actually I erased it. So this is one of the key inputs in all these stories. But of course, usually when you wanted to solve some questions, you need some other input. Okay, so these are, I hope I have provided enough motivation. So, but for the rest of the lectures, I will focus on one working example. So instead of treating complete general theory, I will discuss a working example which fits into this category. So the reason I like this example, or I wanted to present it here, is because the question itself is completely classical. And even in the question, there's nothing to do with the decomposition theorem, the perverse sheaves and these things. It's a completely topological question. And you can see through this example where how these tools can be put together to get a solution to it. A working example. So, and as I said, at the end of the lectures, to prove these results, it requires many tools. But at the end of the lectures, I hope to present a full proof of it. So this example only concerns planar curves. So let's see. So if we consider, so in algebraic geometry, one of the first object we look at are curves in CP2. And we consider, if we consider a curve in CP2, which is a degree D and smooth, so then it's, by the very first course in algebraic geometry, we know this is a Riemann surface of genus D minus 1 times D minus 2, half. Yes. And also we can consider its Jacobian variety, which is the abelian variety of dimension GC. Okay, so this is, for one curve, we have all this data, and we can, again, we can vary C. So we get, so DH, this is the linear system of degree D Planck curves. We'll consider all of them. But well, some of them are nicer. So there is an open subset which parameterizes smooth curves. So this is a smooth curves. Okay, we consider all degree D curves and pick those which are smooth. This is the Zariski open condition. And then we also have the relative Jacobian. So I will use a notation JC and chi over U. So this parameterizes pairs where you have a Planck curve of degree D and a line bundle on these Planck curves. So you vary these curves in this family U, and then you consider a line bundle, and that chi tells you which component you take. So because the line bundles have different degrees, this will be a disjoint union of infinitely many components, and I fixed the degree equivalently. I fixed all the characteristic of the line bundle. I fixed this to be chi. Okay. In other words, we just consider a family of Jacobians of the smooth planar curves with a fixed degree. Okay, actually, for this spaces, for this space, there is a very classical compactification, which was first, I think, considered by Le Boudier and Simpson. So the compactified JC chi, which one of the ways to adding boundary is to tell us that when the curve goes beyond this smooth locus, when the curve becomes singular, then what kind of sheaves you want to put on it to serve as the limit of the line bundles we considered here. So this space is compactify this, and this space is this space was later discovered to underline enumerative geometry of log and local P2. So this is a rich subject actually in enumerative geometry, which has been studied in the local situation. The local P2, this is fits into the framework of Maulik-Toda, and in the log setting, the connection to the log setting was actually more delicate, and this was studied by Boussu, who was the speaker last week. Okay, let me describe the space and the result I want to prove. Okay, first let me introduce you the modular space. Actually, this has similar flavors as the modular spaces I described earlier. So in the smooth locus, you have something nice, and they introduce certain boundary. And you see that actually for both the perspective of enumerative geometry, like in the log and the local cases, the boundary actually matter a lot. So certainly the boundary will be very crucial in understanding the invariance. Otherwise, without considering the boundary, the invariance would be wrong. So it's very important to study boundary. And let me denote the modular space by M, D, and chi. So the D stands for degree, as we saw from the beginning, and the chi is the Euler characteristic. This one, this is the same chi. Okay, so this compactification is actually very simple. So we consider coherent sheaves on P2. Satisfying that F is pure of one-dimensional. Such that, of course, you want to impose the stability condition on the boundary, and the stability condition is just the slope of stability, one of the first stability conditions people study. So you want that for any subsheaf, such that for any subsheaf, the slope is smaller, or not greater than the slope semi-stable says that for any subsheaf, the slope is no greater than the original sheaf. So of course I tell you what the slope is. The slope of a sheaf, a one-dimensional sheaf, would be, you take the Euler characteristic. It's just you only have two invariants to consider. One is the Euler characteristic, the other is the first Chern class, and intersecting with the polarization of the P2. Okay, so it's the standard slope. So this is a very classical modular space, and it's been studied for decades. So it's first, this is by GIT construction, this is a projective variety of dimension d squared plus 1, and it is smooth. Again, all these are given immediately by the GIT analysis. It is smooth if and only if there does not exist any strict semi-stable, which is equivalent to that the GCD of the degree and Euler characteristic is equal to 1. Otherwise, there will be strict semi-stable. Where? What? D, okay. Yeah, so yeah, to compactify this, yeah, thank you. So, yeah, sorry. Let me, so the feeding support, so the supporting cycle of the sheaves is of degree D. Sorry, this is ugly here. Yes, D and the chi is just it's just topological data, namely here. So these modular spaces compactify those. So the supporting degree D curves and Euler characteristic of the sheaves is just chi. You fix some topological data extending the ones above. So if the supporting curve of F is smooth, then it's just line bundle of this Euler characteristic, and then but there are more complicated boundary thing. Okay, so so this is the modular space which parameterizes Jacobians of Planck curves, and so the conjecture of Boussu a few years ago is that, okay, so here the topology of this modular space depends on two things, right? One is the degree, and the other is the Euler characteristic. And the Boussu's original motivation is so the topological invariance of this modular space is actually closely related to like the consideration of a Takahashi conjecture, the Gromov-Witten counts for log K3 surface, the P2 relative and elliptic curve, and then he used the scattering diagram to verify that actually found many symmetries for the cohomology, the Betti numbers of these modular spaces, and he conjectured that, okay, so if you consider, so I mean, for any choice of D and chi, I mean, maybe some of them will be smooth and some of them will be singular. But if in the singular case you consider the intersection cohomology, which is more, it's a more natural object, and you can Boussu conjecture that the intersection cohomology as a Q vector space, this only depends on D, which is obvious because the just the dependence on D is obvious because the dimension depends on D. So obviously, if you consider a different D, then certainly this will be a different graded vector space. But you conjecture that this is actually is independent of chi, so only depends on D. And this phenomenon nowadays is called the chi independence. Okay, so the main result that we hope to present a proof, or at least give the idea of the proof, there are two results. The first one was proof with Davesh-Maulik. About 5 years ago, and very recently there is also another proof by Gorenik with Ziegler, using very different techniques. So the first conjecture, the first result is this is true. The conjecture is true. Okay, so in particular, the topology of this modular space, no matter actually whether it's singular or smooth, it doesn't matter. I mean, if you fix the D, for many choice of chi, the modular space will be smooth, and many other choice of chi, the modular space was singular. It doesn't matter. The cohomological data is independent of D. This is the first thing. And the second theorem, actually tells you what these numbers are, how this is dependent on D. So in the P2 case, this was first verified by Yao Yuan, and then so a proof in the line as I introduced earlier using the decomposition theorem was given by in the joint work with my student Wei-Te Pi, myself, Face, I think he's here, and Fei-No Zhang. And but there's another, for the statement I'm stating here, there's another proof also reasoned by Guo and Wu using complete different method. Okay, the theorem A says that the invariance, the topological invariance, only dependent on the choice of D, and the theorem B tells us that asymptotically this even does not depend on B, does not depend on D. So as a Q vector space, each intersection cohomology stabilizes to the singular cohomology of the simplest modular space we can imagine constructed from P2, which is the Hilbert scheme of points. So you start with P2, and you consider Hilbert scheme of n points. You know that if the n is large enough, then for every hk, the cohomology stabilizes, and this will be the cohomology of this one. So more precisely, so for every fixed k, the intersection cohomology of MdK, dk will be as a Q vector space will be the singular cohomology of the Hilbert scheme of endpoints on P2, as long as d is greater than k half plus 2. So if the degree is large enough comparing to the cohomological grading, then the cohomology does not depend even on d. It stabilizes to the corresponding cohomology for the Hilbert scheme. And of course, you want this n to be large enough. So, and the latter was, of course, calculated by Goetsche's formula explicitly. So this is a relatively satisfying answer to this topological question concerning this modular space, which lies in the crossroads of classical geometry and enumerative geometry. That more or less it says roughly that the topology asymptotically does not depend on both d and chi. It stabilizes. So at the first glance, these statements has nothing to do with the things I talked about at the beginning, right? I talked about, okay, we consider a fibration whose general fiber is abelian variety. Okay, you can imagine what's happening. So there is an abelian fibration structure associated with these spaces. I will explain. But then, okay, I think it's not, at least to me, at the first glance, it's not so obvious to see that this fits into the phenomenon that the boundary does not destroy things. But actually it is. So I will explain at the end that using the same line of the proof I summarized for the examples earlier, then this actually is an immediate consequence of that. So, okay, so just last, I'm also giving the second lecture, right? Yes. Yeah, okay. No need to rush. So let me finish by giving some remarks. And then I will, starting from the second lecture, we will change the gear. We will move from these concrete examples to some abstract machines. So we will discuss the decomposition theorem of BBDG. Sure. What is what? Yeah, so very good question. So where n is large enough, this is actually immediate consequence of Goetsche's formula that the Betti number stabilizes also. Yeah, well, yes, exactly. Okay, right. Yeah, so, yes. Okay, some remarks. And let's, after some remarks, we conclude the first lectures. So the proof with Davish about theorem A and so our proof of the theorem B are both via the decomposition theorem and the support theorem. Actually, it's a little surprising to, of course, so here, actually, this is, to me, this is an interesting phenomenon that the decomposition theorem and the support theorem actually can help us to not only to prove identities, but also to calculate numbers, to calculate explicit invariants. So in our proof, actually we showed a refinement of theorem B, but it will be seen immediately from the argument itself. So let me just, I'm not introducing the notation now because I only have 1 minute, but let me just say it. So the dimension, we should not only that the stabilization for the cohomology, but actually for the cohomology with a natural filtration called perverse filtration. So So MD chi. If you fix the L and the K, where L is a perverse filtration, and this filtration plays an important role in enumerative geometry for local P2, for example. And this stabilizes as a Q vector space. So not only that the dimension of this one stabilizes, but actually each piece of PL stabilizes. And moreover, and when the D and chi is co-prime, then the perverse filtration this stabilizes to a very precise filtration on the singular cohomology called the Chen filtration. So it has a very precise geometric meaning what this stabilization is talking about. To so-called Chen filtration. And lastly, let me just write in words. Yeah, just maybe let me finish here. And Guo and Wu's proof, they did not treat this the refinement, but the proof itself is very interesting in the sense that they his proof of theorem B uses Gromov-Witten theory. So by a correspondence between this number, topological number, and the Gromov-Witten theory for the log P2, that they managed to attack the question completely on the Gromov-Witten side and using degeneration formula, and they actually can get a formula like this. Okay, so let me finish the first lecture.